Hello, my name is Heitor and I'm from the University of Leeds. Today, I'll be talking about an alternative compaction representation to be applied in waste materials based on void and water ratio. I would like to start by acknowledging the other contributors of the paper, Professor Buddhima Indraratna and Professor Cholachat Rujikiatkamjorn from the University Technology Sydney. This work was a spin-off of a funded Australian Research Council, so I would like to take this opportunity to acknowledge their support, their financial support through a linkage project. Also, the materials that were supplied for the project, namely coal wash and steel furnace slag, were also provided by the partners in the project, and their technical advice as well as technical support is also much appreciated, and the industrial partners are listed here as well. So basically the problem is that most of the times we use natural materials to build compaction fields in numerous construction projects. However, most of these materials relied on coring activities. And as listed in the slide, you have a little illustration here on how it looks, on how a quarry looks. These particular types of activities have substantial impacts in terms of carbon emissions, the energy that is being used, land use, and also may destroy unique karst habitats. And meanwhile, we have numerous industrial waste materials such as steel furnace slag, coal wash, and tires represented in the slide that could be potentially used as alternative fill materials. However, these materials, especially their performance, is not very well understood, and the main reason for that is because its properties differ quite substantially from natural fill materials, and that creates a big hindrance for their application. However, the solution for this conundrum is basically to connect different circular economy loops, namely to take the residual waste from mining and industrial sectors that are now currently being landfilled and use that as a raw material for field construction. And what I'm going to present in this particular talk is in relation to how do we deal with these artificial synthetic materials and use established concepts for their application in construction projects. So one of the most common characteristic when it comes to compacted materials and fills are its compaction properties. And normally we represent compaction characteristics or properties via using a compaction curve, and we typically plot that within the dry unit weight or density versus water content space. However, for these materials, because they are quite different, specifically their specific gravity, using the conventional representation may lead to erroneous assumptions. And the alternative representation that I'm proposing in the paper was the use of void ratio in lieu of the dry unit weight, and the use of water ratio in lieu of water content. And you have illustrated here the definitions of both void ratio and water ratio. And these were just basically taken from simple weight volume relationships. So basically, the key message here is that in this representation, the first thing it changes is that we are able to evaluate the densification of the material. Say, for instance, if you look at this first example where we have steel furnace slag and coal wash, you'll notice that in the conventional representation that is sitting here on your left, the steel furnace slag appears as the highest curve in the diagram. However, if you change over to this new representation based on void ratio and water ratio, you notice that the same still furnace slag, 100% furnace slag, actually plots the lowest in the mixes. So that seems to indicate that in this representation, the largest dry unit weight is actually achieved because of the highest density. For instance, here for reference, I've actually included also the specific gravity for steel furnace slag, so that's 3.34, which is substantially higher to that of soil, for instance, and 2.27 for coal wash, which is slightly lower than what we would expect in a soil. But despite that, you notice that the degree of densification, that means the pores in the mixtures, are actually better captured in this new representation. Furthermore, you can see that in the conventional representation, dry unit weight and water content, you notice that the compaction curves are relatively flat. However, when you use a representation where you look at the void ratio and the water ratio, you'll see that the curves tend to approximate or illustrate the typical compaction behavior that would be expecting, a kind of a bell curve. Furthermore, in the conventional representation, if we were having mixes of materials with different specific gravities, that means we would need a set of curves to illustrate the degree of saturation equal 1, or the zero air void line, as well as other degree of saturation lines. However, if you use the void ratio and the water ratio, because the specific gravity is included in the way we calculate void ratio and the water ratio, the degree of saturation lines are unique, so it doesn't depend on the specific gravity. So it can also be, this representation is also advantageous from the comparison point of view. Another example, also published by Malasave et al. In 2012, is using steel slag fines and dredged mud. So similar observations here. However, because it's mixing with steel dredged mud, fine grain material, there are less differences, especially in the for instance, for the 100% steel furnace slag and the lower percentage addition of dredged mud. So again, plots higher and higher, but we see a little bit of a difference when we come to the values where we have higher percentages in dredged mud. And you can see here, not notoriously, especially for the 50-50 and 80-20, in this representation we obtain similar degree of densification, whereas if you use the conventional representation, it actually indicates a different it would indicate a different degree of densification. Here we have another example, and in this particular case we have a mix of black cotton soil and fly ash. Again, you can see that the materials are quite far apart, and we have also the same problem with the different specific gravities and having the different mixes. However, when we plotted in the void ratio and the water ratio representation, we can see that the degree of densification is actually quite comparable. And also the value that presents the lowest value would be the 100% fly ash. That's also common in this representation. And you can also see where are the mixes, the wet sides. We can actually easily identify what would be closer to the degree of saturation 1 and where would be the optimum value, whereas here it seems to vary a bit. Again, this data was published by Mir and Sideran, and it kind of illustrates the robustness of using this alternative representation. So basically, the final slide is for the conclusions. You know, when we are using waste materials, these materials are synthetic, are artificial, and often have very different properties. So it calls for some changes in project delivery. So the typical end product specifications need to take that into consideration, especially when selecting the different optimal blend ratios. It allows the different blend ratio intensification levels, this new alternative compaction representation. And obviously, you know, what I've shown here is just the compaction data. We also need to be mindful that that alone does not provide a full story of how the material is likely to behave in service. So further tests need to be conducted. However, we do, looking at the degree of densification, we can extract similar observation that we would for natural materials in terms of their performance. And obviously, when using these materials, it's necessary to conduct a more comprehensive study to characterize their shear strain behavior that is appropriate with the envisioned application. Thank you.